Welcome back. It's time for video 4, which will be our last video from this particular PowerPoint as it relates to the notion of linear programming and a process for maximization. So we're going to go back and I'm going to pick up a couple of slides that you saw at the end of video 3, just as a bridge to get us across the videos. So let me go ahead and share this PowerPoint and we'll go from here. All right, if you remember, the last thing we did was we created a system of constraints and we created an objective function that contained what it is that we sought to maximize. So this was our set of constraints, our system of constraints. We needed to send at least 0 medical kits, at least 0 containers of water. And the other 2 constraints came in based on capacity of the plane in terms of cubic feet and the amount of pounds that the plane could handle, and wherein each of the particular variables had a certain pound requirement as well. So we were going to then graph that, which we didn't do on the last video. We will on this, but we did spend a moment. We created the objective function that talked about how many victims we'd be able to aid based on this flight and how many of each of those variable things that we were sending, medical kits and containers of water. So that was our objective function. And again, if you want to call it something other than NV, that's a bit verbose, possibly. Just V for victims or N for number would be just as fine. Okay, so your next step would be to actually draw the graph of the system of constraints. So I'm going to show you that on our next slide, and it's a little hard to see. Okay, so we'll walk through the notions together. One of the constraints said X has to be greater than or equal to 0. Well, the line X equals 0 is the vertical line that is actually the y-axis. So you can kind of see an orange line on the y-axis with an arrow down there seeming to be pointing to the right to indicate the values that are in fact greater than 0. Values for y greater than 0 get you the x-axis. That's where y is equal to 0. It looks like that line might be green. And again, it's hard to see. It's on the bottom of the slide. Why is that arrow pointing up? Because again, that first inequality in your system of constraints said you needed greater than or equal to 0. The other 2 constraints are referencing the poundage and the capacity in terms of cubic feet. All right. So there was our system of constraints. And in both cases, for the last 2, you had less thans. So you're not surprised that the shading relative to both of those goes down. So it makes it a little clunky to look at, but what you again seek for the solution to that system is the portion of the grid that picks up all 4 shadings. All right. And if your eyeballs are swimming, I can kind of understand that. So what I opted to do was take that feasible region, which is just the area on the grid that satisfies all 4 of those inequalities, and I just chose to enhance it or blow it up or make it a little easier to see. So I'm going to do that for us on the next slide. But what you have here is each of those 4 inequalities graphed on the same grid. And now the goal is what portion of that grid picks up all 4 shadings. All right. So here's the blow up. And what you find is that the blue shaded region is the area of the grid that picked up solutions or intersections, if you will, to the shadings of all 4 of your inequalities that comprised your system of constraints. So your next goal in life is to find out the ordered pairs that are the end points of that region. So if you look at it critically, it looks like, okay, 0, 4,000 is going to be 1, 0, 0 is 1, looks like 6,000, 0 is 1, and it looks like there's one at 4,000, 2,000. So those represent possible solutions to maximizing your objective function. They also represent possible solutions to minimizing your objective function, but we didn't seek to do that in the context of this problem. So to finish, you need to identify those ordered pairs for those corner spots. All right, so we have them in our possession. There are, in fact, 4 of them, and I just listed them on this slide for us. 0, 0, 6,000, 0, 4,000, 2,000, and 0, 4,000. And to finish our problem, what we will do is we'll take each of those ordered pairs one by one and plug them into our objective function. And we'll look at the value for how many victims we were able to aid. Now look, that first one's kind of sneaky. If you're sending no medical kits and no containers of water, you guessed it, my friends, we're going to help no victims. All right, but it's not invalid mathematically. It's just kind of sad. So there's your objective function. Using the 0, 0 endpoint, you notice that we aided 0 people. Well, that better not be our maximum, or this is a pretty futile attempt. All right, 6,000, 0, which was another one of the endpoints for the feasible region. Plug and chug, that's all it says. 6,000 is going in for X, 0 is going in for Y, and you notice that in that case, we would have aided 36,000 people. Sure beats 0. Whether it turns out to be the max, we'll find out as we check our last 2 ordered pairs. This one's 4,000, 2,000. There's your objective function. So 4,000 is going in for X, 2,000 is going in for Y, plug and chug. Oh, that's bigger. So in this context, if we send 4,000 medical kits, 2,000 containers of water, we would be assisting or providing aid for 44,000 victims. That seems to be the biggest so far. One still to go. Whether or not this becomes bigger, we'll have to plug and chug. There's your objective function. 0 goes in for X, 4,000 goes in for Y. Not bad, 40,000 victims aided. All right, so now you have all of your ordered pairs evaluating your objective function, and it looked like the biggest possible value for your objective function, your maximum, if you will, the solution to the challenge, if you will, occurs if we send 4,000 containers of water and 2,000 medical, oh, I'm sorry, I said that backwards. 4,000 medical kits, because 4,000 is X, 2,000 containers of water, in which case we would be able to aid 44,000 victims. So that is the final solution to the linear programming problem. So it's not difficult to do. Graphing can be a pain. You know, we got some big numbers there in that system of constraints. So scaling on your grids can be a hassle. Okay, problems officially wrapped. Some thoughts for you to think about. If you're going to graph that system of constraints, scaling matters. All right, you might have to pick a scale that's convenient for what you're doing. What's going to happen eventually here is you and I will realize that it wasn't the graph so much that we needed as it was the ordered pairs on the corner spots for the feasible regions. So we could have simply looked at systems of inequalities to generate where those lines intersected and found those ordered pairs by solving systems. So you could kind of sneak in a side door there if you needed to. All right, what's going to happen as we proceed through this unit is we're going to figure out how Excel can play a useful role as a tool for us in this process of maximization. So the next PowerPoint we'll look at will be how you and I can incorporate Excel into our process of linear programming, thereby making less of a reliance on the graph. All right, wraps down our first look at what happens in linear programming. There is a set of problems for you in the Moodle folder that you and I will look at. In some cases, all you have to do is just solve a system of inequalities. In some cases, you'll have to interact with what is a linear programming problem. We're going to get Excel involved soon in terms of trying to figure out how it simplifies our processes in terms of attacking the concept of linear programming. So will be another PowerPoint coming your way with some more videos to get that information out to us, and we'll proceed from there. This wraps PowerPoint number 1 for Unit 5, linear programming. We'll be back soon with how you and I can use Excel in the process. See you then.